All right, everyone, thanks for joining my CMake presentation here. So with this presentation, my aim is to provide a few things. First would be some background information on why we're moving to CMake in the first place, introduce some of the basics in terms of CMake syntax and concepts, but obviously it's not meant to be a full reference documentation for all of CMake. Finally, provide a high-level overview of some of the OpenJ9 and OMR specific mechanics that we've built up in CMake. So what's the motivation behind the move? Well, so as you may know, UMA is currently in the process of being deprecated. The idea is to encourage external contributors to the project. Currently, the number of people who understand the UMA build system and are capable of maintaining it is limited, and they're all either IBMers or ex-IBMers. So by moving to a more standard tool chain, we can remove an additional entry, since it's possible that contributors are already familiar with CMake, and if not, there's already a rich set of existing documentation that they can learn from. And as part of the CMake migration, CMake default for JDK 11 on most platforms, the only holdouts being ZOS and cross-compiled builds. So why CMake specifically? There are a number of other build system tools out there, but CMake is quickly becoming the system of choice among new projects, particularly C++ projects. In addition, CMake has excellent cross-platform support. Out of the box, it already supports AIX, and our internal ZOS port is really pretty minor. It's just a tweak of the Lexer to handle Epsidic. Also, although we don't fully use it in J9, CMake comes with a powerful suite of tools, which include CPack, which is a packaging installation generator, so it can generate tarballs and installers from your generated binaries. CTest, which is a testing framework, and that we're actually using for the OMR tests at the moment. And then C-, which is their web-based software testing server. Finally, we're starting to see some significant support from third-party tooling for CMake. So as an example, while CMake can generate project files for Visual Studio, in Visual Studio 2017 and up, they can directly open the CMake files. And JetBrains CLion actually has CMake files as their native, well, one of their native project formats. So what is CMake specifically? CMake is a cross-platform build system generator. So you give it a description of your project, and from that, it can generate files to be used by a number of different build systems, including various flavors of make files, Ninja, and assorted IDE project files. And as I mentioned before, some IDEs are now actually directly supporting CMake, so you don't need to do the intermediate step of project generation. So let's dig into some of the syntax of the CMake language itself. The language itself is pretty simple. It consists of a series of command invocations, each terminated by a new line, where a command invocation is just the name, a name, followed by a set of parentheses enclosing some white space separated arguments. Of note here is that command invocations don't return a value, and as such, you can't nest them inside arguments to other commands. You cannot nest command invocations inside arguments to other commands. Variables. Variables can be set using the set command. So in this example here, we're setting the variable named foo to a value of bar. Variables are always strings. So quotes are used only for capturing white space within an argument to prevent it from being split up into multiple arguments. And as we can see here, we're setting foo to the value of 42. And it doesn't matter if we put it in quotes or not, it still ends up being a string. Variables can also hold lists. Internally, those are represented as just a string with semicolons to delimitate the items in the list. So in this example, both commands will result in foo being a list with the values of 1, 2, and 3. Variables can be substituted by using the $ curly brace syntax here. So, you know, your standard hello world type deal substitutes the value of the name variable in there. It's important to note that expanding a variable outside of quotes, for an argument outside of quotes, will result in expansion into multiple arguments if the variable was a list. So in our example here, we have a variable with the list ABC. In the first line, there's no quotes, so expanding it is the same as calling foo with 3 separate arguments, A, B, and C. Whereas in the second form, where you wrap the expansion in quotes, it calls foo with only 1 argument, which is the semicolon separated list. Variables are scoped. As you would expect, scope lookup walks from the innermost scope to the outermost scope. And by default, using the set command to set a variable will set the value in the innermost scope, even if that variable by the same name exists in an enclosing scope. If you pass the parent scope keyword to the set command, the value is set in the enclosing scope. This is how typically functions return values, is they would take an argument of a variable name and then use the set command with the parent scope argument to set whatever return value they want up on the parent, or in the callee. New scopes are created when entering a function or when entering a new directory using the add subdirectory command. And when new scopes are created, they get initialized with a clone of their enclosing scope. Cache variables are variables that are used to persist values across runs. They get stored in the CMake cache. Generally, they're used to store user configuration, for example, enabling some build option, whatnot. But they're also used to cache the results of expensive tests, like checking if a library exports a certain symbol, finding the include path where you can find a certain header, things of that nature. On the command line, there can be specified with the -d var equals value syntax, or from CMake itself. It's the same set command, but it now takes a cache keyword followed by a type, which can be bool, file path, path, string, internal. This is really just used for pretty input selection. If you're using the CMake GUI, it doesn't do any validation on that, so just be aware of that. And then optionally the force keyword. By default, using the set command like this will not overwrite an existing cache value unless you specify that force option. So it's generally kind of used to set a default for the value, which the user can then override on the command line if they want to. So in the example here, we have from OMR, we have an OMR JIT builder variable, which will control if you build JIT builder or not. It will default to off, but of course, then the user can specify on the command line if they want to. So central to any build system are targets. CMake has 3 main types of targets: libraries, executables, and then custom targets. Libraries are introduced using the add library command with syntax shown here. Pretty simple. It takes a name, a type, and then a list of sources. Type can be static, shared, object, or interface. Static and shared, I'm assuming, are self-evident. And object and interface libraries are the interesting ones here, and I'll get to those in the next couple of slides. Executables, added with the add executable command. Same basic syntax, other than it doesn't take a type argument. And then you've got custom targets. The syntax here is simplified syntax because the full range of options it takes would probably fill this entire slide. But it acts like a phony target would in Make. So it's just a named target that doesn't necessarily generate an actual file, and other targets can depend on it, and likewise, it can depend on other targets. So now that we have the targets, we need some way to configure them. So here we have the set of commands for the various options that you would want on targets, your include directories, link libraries, things of that nature. They all have a fairly uniform syntax where you give it the target name, then an access specifier, and then some list of options. Sorry. So the option access specifier, can be private, interface, or public. Private applies the options to the specified targets, and that's it. Interface options don't apply to the target in question, but rather get propagated to consumers of the target via linking. And public options behave as a union of both private and interface options. So as I mentioned, linking against a target can propagate interface options. The way this works is, suppose we have some target A that links against target B. B's interface options are applied to A using the same visibility that was used to link against B. Let's say A links against B privately. B's interface include directories are added to A's private include directories. Conversely, if A publicly links against B, then B's interface include directories get applied to A's interface includes as well as its private include directories. That's a very powerful part of CMake in terms of propagating requirements between targets. In addition to these commands, there's also a number of variables that can be used. For example, there's CMake CXX flags. This is largely a holdover from before the target-specific commands existed, and using them is generally discouraged in favor of using the per-target commands that I just showed, partly because there's less chance of accidental bleed over if you have multiple unrelated subprojects. You don't risk one accidentally modifying the options of the other. And also, if you use the given commands that I showed, CMake has some built-in tools for actually tracing how certain options get applied to other options via the whole linking situation. You can actually trace, well, A linked against this, which linked against this, and that you can follow the chain of dependency there of how those properties get propagated through. So getting onto the object libraries, follow the normal rules in terms of compile options, include directories, etc., as all the other libraries. However, CMake will stop short of the actual, where it would be a call to an archiver or the linker in terms of a static or shared library, just stops there. And so you use object libraries as a convenient way to refer to some set of objects. So where would you use something like this? Well, in our code, we use it for both port and thread libraries. So OMR has both port and thread library, and we define OMR port obj and OMR thread obj, and it would then use those objects again to build its own port and thread libraries. However, J9 wants to add some extra source files to the OMR port and thread libraries. So rather than recompiling all those source files again, it takes the OMR port obj and then uses that list of objects and appends its own set of objects to that to generate the J9 port library. And then interface libraries, as the name might imply, can only have interface properties specified on them. So, interface sources, interface compile options, and the like. So the way you kind of have to think about them is a named collection of options that you want to propagate to other targets with linking. So as an example, in J9, we have J9 VM interface, which here we set a number of our common include directories, and then we'll link all our targets against J9 VM interface so that they all inherit those common include directories. Excuse me. In addition, just like make, you can specify custom build rules. Again, here we have a simplified syntax. These will specify how you can build a file from a given dependency, and they act just like a normal rule in make. Further targets which depend on those files will then automatically depend on the generation step, just like you'd expect. The one caveat here is that due to some quirks in the way CMake is implemented, this doesn't work properly if you define how to generate the file in a different directory from where you're trying to use it. You generally can work around this by then wrapping the generated file with an add custom target, and then having the target you want depend on that on the custom target instead of the generated file itself. So in terms of factoring up your CMake code, you've got two options. There are functions and macros. The function syntax is here. You've got to start with a function, command name, then the arguments are the name of your function, and then some list of declared arguments. And it's closed out with the end function, and you can optionally give it a name. And if you do, CMake will check that the open and close match names to make sure you don't have some mismatched blocks somewhere in your code. Functions, as I said, introduce a new scope, and arguments exist as variables, which kind of sounds obvious, but it's contrast to the way macros work. When you call a function, CMake will validate that you've passed all of its declared arguments. However, it will allow you to pass extra arguments. So the declared arguments are really sort of more of a minimum amount of arguments that you pass, not a definitive signature of the function. So on top of the arguments, CMake provides you with a number of common variables for both functions and macros. argc, the total number of arguments passed. argv, which is a list containing all the arguments that you've been passed. And then some alias function variables, argv1, 2, etc., for accessing the nth argument. And then argn, which is the more interesting one. It's a list of arguments that were not declared. So it's your extra kind of variadic arguments, if you will. Then we have macros, same basic syntax in terms of the CMake side. In contrast with functions, macros don't introduce a new scope, and they are expanded into the call site at parse time. And kind of as a consequence of this, your arguments aren't real variables, but just kind of placeholder names for use in the expansion process. Most of the time, this doesn't really make any difference. The only time it really does is when there's a function which expects the name of a variable in order to return some value or something of that nature. And then it won't work, because if you specify the name of an argument, it's not a real variable. So you just have to be conscious of that one. So, oops. I have a small example project here. It consists of main executable and a small shared library that we're building. So, showing the first way you might configure your project, here we have a config.h.in, very much the style that you would do it in AutoConf. So we have a CMake define here, which is just like the pound define for an AutoConf configured header. Based on the value of header config option, it will either expand to defined header config option or a commented out undef header config option, depending on if this value is true or false in CMake. Then for our library, we also have an include directory with a public header. So here we're just supporting some library function, which returns a const char. And then what we want is, because this is a shared library, we have to annotate it with DeclSpec DLL export or import on Windows. So we have, if defined win32, and then if we don't have this library internal defined, it's going to be an import function. Otherwise, it's going to be an export function. And so we want, to define library internal when we're compiling the library, but not when we're consuming it. And the library itself, very, very simple, is just, depending on that config option, either returns a string saying the value is on or off. Then our main library here, very simple. We have a different config option here, which we'll set on the command line with a just -d my config option when we're compiling. And again, it just prints out a different string of whether it's on or off, and then prints out the string that's returned by the library function. So in terms of the CMake code to build this, at the top level here, we have a CMake list.txt. There's some boilerplate here. CMake minimum required. It should be pretty obvious. It's just saying we require at least version 3.4 of CMake. The next one is this project command, which introduces that we're creating a new project called example with version 1.0, and that we want the C++ language. What this will do here is then when CMake runs, it will trigger off finding the C++ compiler, running some ABI tests, a couple other things like that. If you leave out this, it will assume you want just C. I think it does C and C++ by default. So here we're setting our default options for our config options. We've got that my config option and the header config option. My config will default to off, and the header config will default to on. Then we have this add subdirectory library, which will cause CMake to look in the library folder for a CMake list.txt. We go there. We're saying we're adding my library, which is a shared library, which consists of, of library.cpp. Then we're setting up our include directories. So our public includes, which will be the current source directory /include, which has our library public.h, because we want consumers of this library to get that added to their include path. And then privately, we have the current binary directory because that's where we will generate our config.h. And as a side note here, CMake has separate concepts of the binary directory and the source directories. It's basically the source tree and the build tree, because it's generally encouraged to keep those separate, just to avoid potentially polluting the source directory, which means that you can have multiple build trees with different configurations, all pointing to the same source tree. And then here we set up the compile definitions. Again, we set this library internal flag to be set up private, just so it's defined when we are building the library and we get that DeclSpec DLL export. And then this configure file, which it takes that config.h.in, and it will generate a config.h in the current binary directory. Going back to the main CMake, we then add our executable with main.cpp, and then publicly linking against my library. Because it's an executable, it actually doesn't really matter if we link against it publicly or privately. It's just, I decided to do it public. And then based on the value of this my config option variable, we will tack on -d my config option to the compile definitions, for example, for the example executable. So in terms of building this, we're in the source directory. Let's make ourselves a build tree. Then to actually run CMake, the syntax is pretty simple. CMake, point it to a source tree. So in this case, just above us. And then let's say we want my config option equals on. Then it runs through, finds the C++ compiler, runs a couple tests, and then it's generated our make files for us. So then building, it's just a simple make. And then we have our example build. Also, we get the standard targets of, we get our make clean. The other interesting one that gets generated for us, we get a make help, which will list all the targets at the top level here. All it should be self-explanatory, clean, depend, rebuild cache. Generally, you don't need to use this. It should automatically trigger. Edit cache will allow you to edit the cache if you don't want to use the command line for whatever reason. And then our example things. Also, it produces, because the main executable up here is finance directory, we have rules to build the object file or a .i file, which would be the pre-processed file, or the .s assembly file. Conversely, if we cd into my library, oh, right, I cleaned, that's not. But let's say we just want to build my library on itself without building the main executable. Just make my library, and it does that. And also, oh, right, it's my library as well. So if we also change the library, we make help in here, we get the same, rules for the library object include and assembly sources. So let's say I've changed my mind now, and I actually want the header config option to be off. We can CMake again, point it to an existing build directory, and say header config option equals off. Reruns, generates new build files, and then make again. And it's created our example. Also, CMake has built-in notion of configuration types. So let's say I want to generate a debug build. I can use the existing tree and then set the CMake build type equals debug. Makes me new make files. And it has a new executable built with the -g option. How can we check this? Well, let's just make clean this. And then, so let's say you need to debug exactly what's going on here, because you want to figure out what commands are being run, etc. You can do make for both equals 1, and we'll do main.o. Here we can see, it's calling the C++ compiler, is giving it that -g option. That's that, or we can make build type release. Now we're getting a release build with O3 and -d and debug. That, so getting back. Getting on to some of the OMR and J9 specific components that we've got. So first, a kind of overview of our important directories. This part is for OMR, but the J9 stuff is structured largely the same. At the top level, you've got CMake, which is all our various CMake bits that aren't CMake list.txt. Then you've got the module subfolder, which has code which is designed to be shareable across different projects, versus some of the code which is tightly tied to OMR, which we put up in the CMake folder. Then under modules, there's the platform folder, where we've organized all the various platform-specific configuration options. And then also there's a caches folder. which hold our CMake caches. Cache files in CMake are just basically CMake syntax files, which get evaluated before parsing the top CMake list.txt. On the command line, you would specify -c and then a cache file. So usually they're just a simple collection of set variable cache commands for setting various defaults, but it does support a significant subset of the CMake language. You can have control flow, things of that nature, but you cannot define new targets in there. For OMR, we're really just using this to kind of set up some default options for our CI builds. And in J9, this is where kind of our build spec files, the equivalent in UMA. So everything that would have been a build spec has its own cache file in here. So moving on to some of our CMake modules. The first important one is kind of OmrDetectSystemInformation. This has two functions. The first will be normalizing the platform info that we get back from CMake. So as an example, CMake system processor might tell us, x86-64 if we run the build on Linux, but if we run it on OS X, it might tell us, AMD-64. So the first thing we do is, kind of normalize all this information and create our own environment variables, or sorry, just regular variables to kind of communicate this back, and so we can have a more consistent experience. The second thing we do here is test some characteristics of the build system. So as an example here, we have our function OmrCheckDLAdder. Pretty simple. It basically just includes a DL function.h and checks if the DLAdder symbol exists. Previously, this code in OMR, this code that relies on this in the port library, was just if-def on Linux or OS X. But here we can actually test if the function exists and switch behavior without having to maintain a list of supported OSs for this. Why might you do this? First of all, it's faster and easier to bring up a new OS, because presumably if we have all our behavior gated like this, it will just check and choose the appropriate code to use based on the particulars of the platform we're building on. And secondly, we can avoid some assumptions about the environment based on the OS. So as an example, a lot of places in the port library will assume that if we're building on Linux, that means we're using glibc, and we can use some various glibc extension functions. However, while that might be the case for our internal builds, that's not necessarily the case for everyone. You could be building on Alpine Linux, in which case you have Musel C library instead. So in general, I like to try and prefer new functionality is checked like this rather than hard coding based on OS. But of course, obviously, there's sometimes where gating on the OS is the correct behavior. Closely related to that, we have OmrPlatform.cmake. This takes the normalized system information that we generated previously and use it to apply our specific platform configs. As I said before, all the platform-specific configs is CMake module/platforms, and there we have it broken out into architecture, OS, and toolchain. So as an example, for an X-Linux build, we would include arch/x86.cmake, os/linux.cmake, and tool config GNU.cmake. The problem here is sometimes it's not always clear where you need to put a certain piece of configuration. As an example, you might need to flag that you set only on P-Linux when you're using XLC. It's like, well, which folder do you put it in? It's not always clear, so sometimes you kind of have to make a judgment call there. Next up, we have OmrTargetSupport.cmake. This provides our two main target wrapper functions that we have in OMR, OmrAddLibrary and OmrAddExecutable. As the names would suggest, they wrap the built-in CMake commands of similar names. But on top of that, they provide additional OMR-specific logic. So depending on like the OMR warnings as errors variable, it will apply WError or whatever the toolchain equivalent flag is to that target. In addition, it handles generating the split debug info and also handling exports from shared libraries, if applicable to the given platform. Then there's OMR compiler support. Basically, same idea, except just for the JIT. We have the create OMR compiler library function, which handles the same basic stuff, but just specially for the JIT. So it will do the special include paths handling that you need, handles the various TR flags. It's also responsible for running the SPP tools if required. From the J9 side, in general, I've tried to keep things consistent there. We just kind of extend the concepts from OMR. So as an example, we have a J9 VM add library, which then does its own specific handling that it needs to do, and then passes the buck onto the OMR add library function. Also, we have the same kind of layout in terms of configuration of splitting things out into OS architecture and then toolchain. But this is much simpler because we only deal with things that are specific to J9, our various kind of micro optimization flags, target architecture tuning, things of that nature. In general, things that might be useful to external users of OMR, I've tried to push down into OMR to keep only really the stuff in J9 as things that really only J9 cares about. And the same basic CMake directory structure follows in OpenJ9, except it's just rooted under the runtimes folder. So how does this all integrate with OpenJDK? Well, the first thing to note is that the OpenJDK build system is still using the autoconf and make infrastructure. That hasn't been CMakeified. So you cannot generate an IDE project for building a full Java VM. The way this is done is in the OpenJDK extensions make file, where we simply call CMake during the make process, and then later on call make into the generated make files. So of note there is the CMake binary directory will be in build/configuration name/VM. So you can poke that for building specific parts of the VM that you want to rebuild, or looking at the cache file, finding whatever object files that you needed to for whatever reason. And then also the list of -D options that we pass to CMake is built up based on information that we've saved when executing the configure script. But on top of that, you can provide extra options if you want with the extra CMake args environment variable, just in case you need to specify something differently that hasn't been put into the extension. Capability hasn't been put into the extensions yet. Excuse me. So kind of in summary, UMA is being deprecated in favor of CMake builds. We are already the default on JDK 11 for almost all the platforms, but OpenJDK itself is still being built with autoconf and make. In CMake, you can use object libraries to reuse compiled objects without some of the drawbacks of static libraries, namely exporting symbols if you're building a shared library, as we are in the port library. Interface libraries can be used to group related options to propagate to other targets. In general, with doing things based on system behavior, you want to actually check the system behavior rather than switching based on OS. And if you're looking for our platform-specific compiler options, you can find those in the CMake module/platform for OMR or runtime/CMake/platform for OpenJ9. Any questions?
Hi, Devin.
Yep.
I got two questions about the CMake. The first one is when I building debugging build, I just bought a JIT, and that was a bigger bigger size of the directory size, because it looks like as compared to the Umar build, it generated a bunch of things which I have no idea if it's a necessary or something out there, or is something related to temporary file or directories. So is it possible to a little bit optimize it to shrink the size in there?
Yes. So I think the issue here is that, so in the UMA builds, even with non-debug builds, if you have DDR, we still generate the debug information for most of everything.
Okay.
The exception is because the JIT has its own separate make files, we don't generate debug info for the JIT. But because it's a kind of a C++ heavy code base, if you do generate debug info, there's a lot of debug info.
Okay.
And in the CMake builds, for simplicity, we generate debug info on everything. So the UMA builds don't generate debug info for the JIT, whereas we do, because just make things more uniform.
Okay.
I'm definitely kind of looking at some of the options we have for potentially disabling that, or going back to our old behavior of not generating a debug info for the JIT, or to keep the compile sizes down. And also, there's a few things in the GNU toolchain that you can do to potentially compress the debug info, and which saves you on disk space and improves memory usage when linking.
Oh, cool. That's very useful. So could you send me out or do leave it in the checkbox so I can check a little bit check it out?
Yeah, I'll try and dig up a link on that and send that.
Okay. Another question about still about with the debug build. So I spot that when you set up the breakpoint, it end up with a little bit couple step forward, and that's breakpoint setup out there. So I'm not sure what happens there, because does it mean the existing debugging option of OpenJ9 is out of date, or somehow already get updated? I'm not aware of that.
Yeah, I haven't seen that one, but I know that a lot of times our handling of the split debug info sometimes does weird stuff, especially where it's packaged now. I can imagine that potentially that gets out of sync.
I just leave the debugging options check in the checkbox. You can see that. I'm not sure some of them probably update or need to update with the CMake.
Yeah. So like I said, I haven't experienced that myself, but if you can open up an issue,
yes,
I'll
because
take
there's
a look
very
at it.
strange behaviors on my side.
Yeah. So yeah, if you open up an issue, I'll take a look at it.
Okay. Cool. Thanks.
Yeah, no problem. Anyone else? All right, well,
last call for questions for Devin. No. Okay. Well, thank you very much, Devin, for the informative talk.
Yeah, no problem.